Hi, I am Akshay Raj. Within this video, we are going to discuss something about external flux linkage. So, I'm saying that this derivation is very easy if you know how to derive an expression for internal flux linkage. So, if you have not seen that video, I will provide the link over here. Go through that and watch the video so that it will be very easy for you to understand this concept much better. Firstly, I will go through the concept. Whenever a conductor is carrying some current, then it produces magnetic field around it. So that magnetic field will be produced around the conductor and inside of the conductor. We have already derived that expression for internal flux linkage because of the flux that is present inside of the conductor, and now we are going to derive the expression for the field that is present outside of the conductor. That means flux present outside of the conductor and flux linkage, that is called external flux linkage. Now let us consider a conductor. So our topic is of about transmission lines, right? So that let us consider this conductor as a transmission conductor. So one of the conductor in transmission line, and it is of about r radius, and we are considering some dy portion over the atmosphere of this conductor. Why? Because it is external to the conductor, right? So that I am assuming some dy portion over here, which is y meters away from this center of the conductor, and here we are having some 2 points p1 and p2. Those are of distance about d1 and d2, and here we will have some magnetization force because of the current that is flowing over here. Now our responsibility is about to derive this expression. So what we need to do means we need to determine firstly what is the magnetization force that is present over here, that is Hx, which was previously derived in that internal flux linkage. Very easy. We need to determine the Hx. Through that Hx we will calculate what is flux density. From that flux density we will derive the expression for how much of flux is present over here, and after that we will keep that flux expression in final expression, that is lambda. Lambda is flux linkage, that is equals to n phi, and the n value will be 1 and phi value will be 5, so that we will integrate, so that integration will give us the total external flux linkage. That is the concept. Let us go through the derivation part. Coming to the derivation part over here, I took a conductor which is having some radius r, and I have taken some dx portion over here, which is x meters away from the center of the conductor, and it is external to the conductor. Why? Because we are dealing with external flux linkage, right? And within this field we are having some Hx, that is magnetization force, and this Hx is due to the current that is flowing through the inside of the conductor. Within the previous case in internal flux linkage, the Hx is produced because of the current Ix from the fractional portion, from the portion that we have considered. But what happened here means this Hx is produced because of the total current that is present over this conductor. It means inside of this conductor. This is the main point within this external flux linkage. Now how Hx is determined means by using circuital law, as circuital law states that the current flowing through the conductor is equal to the line integration of the magnetization force. It means my I is equals to line integration of Hx dx, and I am keeping the limits as 0 to 2 pi x. If I integrate this value, then I is equals to integration of 0 to 2 pi x. Hx will become here, and directly it is dx. Now I is equals to Hx, so x limits are from 0 to 2 pi x. Now I is equals to Hx 2 pi x. Now what is Hx? If Hx is subjected here, then I is equal I by 2 pi x. We were determined what is Hx. Now what is our duty means we need to determine what is the flux density over here. For that we were having some formula, that is Bx is equals to mu Hx. Here mu is equals to mu naught mu r, where mu r value will be 1 if we consider the medium as air. Since it is air, then mu r will be 1, therefore mu is equals to mu naught. Therefore Bx is equals to mu naught and Hx will be I by 2 pi x. Now what we need to do means we need to determine the total flux that is covering over here. That is d phi. As it's differential distance, therefore we are considering the flux over there is also differential, that is d phi, and this will be equal to the flux density Bx multiplied by the area. The Bx value will be this one, that is mu naught I by 2 pi x into area is, the area will be this dx into the total length of the conductor. It means we have considered a 1 meter length of conductor, therefore area will be L into B such that B will be this dx and length will be L, that is 1 meter, as dx into L is 1, so that I am keeping here 1. Now mu naught I by 2 pi x dx is our d phi. Now we know that the flux linkage lambda is equals to n phi, but here what we have derived, here we have d phi, so that keep lambda x is equals to n d phi x. In transmission line, the n value, number of turns will be 1. Why? Because we are considering only one conductor, so that keep 1 over the n and substitute this dx value over here. Therefore lambda x is equals to mu naught I by 2 pi x and dx. This is the flux linkage that is going to happen over that particular portion what we have considered. But we need to determine the total external flux linkage, so that what we need to do means we just need to integrate the value that we have derived down. Thus that integration of this whole value with respect to dx will be the total external flux linkage. And from where to where we need to derive means this is the radius of the conductor r, and we need to derive up to a distance of d2. Here this d2, or let us consider this point as d, is a distance that we have considered from the center of the conductor, right? So let us suppose to call this d2 as d minus r, such that we will have some distance from here to here. Then we will have limits like this from r to d minus r. It means we are calculating the total external flux linkage from the surface of the conductor, that is from point r to the extreme point of the external atmosphere where our field exists, that is d minus r. Between these 2 points we are determining the flux linkage. Now if we do this small integration means what we will get, we need to substitute this lambda value here. Therefore integration of r to d minus r, lambda is equals to mu naught I by 2 pi x dx. Other than x, everything is constant for me, so that let us keep the constants away from this integration. Outside of this integration, d minus r, this is mu naught I by 2 pi, 1 by x is remained over here, and dx. If integration of 1 by x is what, that is log x, mu naught I by 2 pi x log x, and I am remained with some limits r to d minus r. Now by substituting these limits, mu naught I by 2 pi x log of upper limit minus log of lower limit. Now in general logarithm, log a minus log b is equals to log a by b. Log a minus log b is equals to log a by b. That we need to perform over here. Mu naught I by 2 pi x log of d minus r by r. If this r value is very less, then this d minus r value will become d. D minus r will become d. Therefore, our final expression will be mu naught I by 2 pi x log of d by r.